Hello and welcome to the LPC1700 product overview presentation. In this presentation, we will cover the following topics: introduction, benchmarks, memory support, key system blocks, power management, peripheral support, and tools. Introduction. In this section, let's visit the following areas: series overview, bridging the ARM7 and Cortex M3 worlds, and finally let's go over the LPC1700 block diagram. LPC1700 series. The LPC1700 is pin-to-pin compatible with the popular ARM7 based LPC2300 family. This allows for smooth migration for ARM7 customers to move on to Cortex M3. The NXP implementation of Cortex M3 has the following key features: Memory Protection Unit, or the MPU. This unit can be a great complement for an RTOS based application. NVIC, the best interrupt vector controller implementation that offers defined interrupt latency. Wakeup interrupt controller that allows fast wake up from power down modes. Flash Accelerator. NXP Cortex M3 devices can execute out of flash with zero wait states. This device has got excellent DMA support that fully enables the high-end serial interfaces like USB, CAN, and Ethernet. With 15 serial interfaces, there is no doubt that this device is tailored for communication. This series has low power operation, and we'll discuss the power reduction modes in the tail end of the presentation. Last but not the least, the LPC1700 is the industry's first fastest running Cortex M3 at 100 MHz. Series overview. This slide shows all the derivatives of the LPC1700 series. Let's break the table into two parts so that you have a better clarity on the offerings. The first set of devices cover the 100-pin package. You can see the different flash and RAM sizes. The LPC1768 is the most featured device in this series with 512 kilobytes of flash and 64 kilobytes of on-chip SRAM. Together with the full flash and RAM configurations, you also get a full set of peripherals including Ethernet, full-speed USB, which has device host and OTG controllers, CAN, I2S, and a DAC. The next set of devices cover the 80-pin packages. Here you can see that the flash size can go from 32 kilobytes all the way up to 512 kilobytes. The LPC1751 is the least featured device in this series with 32 kilobytes flash, 8 kilobytes RAM, and equipped with USB full-speed device. Bridging two great families, ARM7 and Cortex M3, we have the strongest mid-range ARM7 portfolio, which is represented by the LPC2000 family. With our introduction of the LPC1700, we wanted to give our customers a smooth migration from ARM7 to Cortex M3. To accomplish this objective, we made the LPC1768 to be pin-to-pin compatible with the LPC2368. This compatibility allows customers to evaluate both the Cortex M3 and the ARM7 based product in the same socket and to choose the right microcontroller for the application. Let's have a brief look at the most featured device of the LPC2300 series, the LPC2378. LPC2378 block diagram. Let's focus on one key point: the dual AHB bus. The Ethernet block is a master of AHB2 and the USB block is a master of AHB1. This key feature allows these peripherals to run with their maximum capacity with minimum CPU intervention. To get more details on the LPC2300, please refer to the respective user manual or the insider's guide, which can be downloaded for free at the NXP website. Let's begin with the LPC1700 block diagram. We have broken up the block diagram into two parts. Let's focus on part 1. On the top we have the Cortex M3 core, DMA controller, Ethernet and USB blocks. On the right hand side are the different internal memories, SRAM, flash and ROM. Interfacing the flash to the rest of the chip is the flash accelerator module. Connecting all the blocks with the different peripherals is the Multilayer AHB Bus Matrix. The LPC1700 uses a Multilayer AHB Bus Matrix to connect the Cortex M3 buses and the other bus masters to the peripherals in a very flexible manner. This structure optimizes performance by allowing peripherals on different slave ports of the matrix to be accessed simultaneously by different bus masters. Let's look deeper into the multilayer AHB matrix. The multilayer AHB bus matrix provides a separate bus for each AHB bus master. The AHB masters include the CPU, general purpose DMA controller, Ethernet MAC, and the USB interface. The matrix provides more flexibility than a dual AHB bus. This interconnect provides communication with no arbitration delays until two masters attempt to access the same slave at the same time. Let's look at the second part of the block diagram, which focuses on the different peripherals. As you already know, the LPC1700 has got 15 serial interfaces. The matrix uses two AHB to APP bridges to connect the different peripherals. The peripherals are neatly divided into two groups, APP slave group 0 and APP slave group 1. The blocks that are shaded refer to the blocks that can be accessed by the GPDMA. The DMA can access some other blocks as well, and the full picture will be available in the DMA section. Bit band regions. In ARM7 and ARM9 CPUs, one could perform bit manipulations on SRAM and peripheral memory locations by using AND and OR operations. This requires a read-modify-write operation, which is expensive in terms of the number of cycles taken to set and clear individual bits and the overall code space required for each bit manipulation. To overcome this restriction, a technique called bit banding allows direct bit manipulation on sections of the peripheral and the SRAM memory spaces without the need for any special instructions. The bit addressable regions of the Cortex M3 memory map are composed of the bit band region and the bit band alias region, which takes up to 32 megabytes of the memory map. Bit banding works by mapping each bit in the bit band region to a word address in the alias region. So by setting and clearing the alias word address, we can set and clear bits in the real memory. The image shows a bit banding example for the SRAM region. All the images have been taken from the Cortex M3 white paper that is published online. Please refer to the shown PDF for more information. LPC1700 bit band regions. This image shows all the regions in the LPC1700 that can be bit banded. The peripheral region is completely in the bit band space. On the SRAM side, note that only the two 16 kilobyte blocks are in this space. The LPC1700 does face competition, but we have several key advantages over our competitors. 100 MHz clock speed, a flash accelerator module that allows for zero wait state flash operation even at 100 MHz. On an average 35% higher performance than leading competitors. The multilayer AHB bus matrix allows for simultaneous Ethernet, CAN and USB operations without bottlenecks. A fully compliant USB 2.0 block with device host and OTG controllers. A memory protection unit or the MPU that allows for separation of processing task and data protection. Fully fledged debug interfaces along with embedded trace macro cell, a Wakeup interrupt controller, very low power, ultra low power real-time clock with a full-fledged calendar function. And last but not the least, we have the latest revision 2 Cortex M3 core. Benchmarks. Here is a brief intro to the Embedded Microprocessor Benchmark Consortium. The EEMBC develops and certifies real-world benchmarks and benchmark scores, which is helping designers to select the right processor for their system. EEMBC benchmarking represents different workloads and capabilities in automotive, industrial, communications, networking, consumer, office automation, embedded Java, network storage related applications, etc. The automotive and the industrial benchmarks were used for the LPC1700. Members of EEMBC include leading semiconductor intellectual property and compiler companies, and for more details please visit their website, which is www.eembc.org. Here is a quick summary of the results. After running the benchmarks, we can show that the LPC1700 is the industry's highest performance Cortex M3 MCU, and we can execute application code on an average 35% faster than the leading Cortex M3 competitor when running at the same clock speed. At greater clock speeds, as expected, we excel. As you will see in the follow-up slide, we are certified by EEMBC at 72, 100 and 120 MHz. Benchmark results. The green, blue and yellow bars represent the LPC1768 running at different frequencies, which are 72, 100 and 120 MHz. The red bar indicates our closest M3 competitor running at 72 MHz. The x-axis indicates the different algorithms and the y-axis indicates iterations per millisecond. For apples to apples comparison, please compare the green bar with our closest competitor in red. You can see that for almost all the algorithms, the LPC1768 running at 72 MHz surpasses in performance by a huge margin. These results bring the LPC1700's performance and its capabilities to a new light. Memory support. Under memory support, we will cover the following topics: internal memories, flash accelerator, booting, and the MPU. Let's revisit the Multilayer AHB Bus Matrix diagram, which shows all the internal memories. We have an on-chip flash which has a maximum configuration of 512 kilobytes. This flash can perform with zero wait states even at 100 MHz when used with the flash accelerator. A total of 64 kilobytes of on-chip SRAM is also available, which is broken up into 3 blocks, one 32 kilobytes and 2 additional 16 kilobytes. This breakup is a key feature since it allows the 3 AHB masters to spread over 3 separate SRAMs that can be accessed simultaneously. This chip also features a 8 kilobyte ROM which has all the APIs for the flash operations. Flash accelerator. Simply put, the flash accelerator attempts to have the next Cortex M3 instruction that will be needed in its latches in time to prevent CPU fetch stalls. Internally, the flash accelerator includes an array of 8 128-bit buffers to store both instructions and data in a configurable manner. The operations within this module are completely transparent to the end user. Programming this block is achieved by a one register configuration, which is called the flash configuration register. After reset, the flash accelerator defaults to the enable state. Software can turn memory access acceleration on or off, or change the acceleration configuration at any time. Following reset, the flash access timing is also set to a default value of 6 CPU clocks. This is considered as a safe setting and will work for any condition. As an illustration, if the application needs to execute at 20 MHz, the timing can be set to 1 CPU clock. And if the application needs to execute at 100 MHz, the timing can be set to 5 CPU clocks. Flash programming operations are not controlled by the flash accelerator, but are handled as a separate function. The booting process in the LPC1700 is similar to the LPC2000 family. The chip offers two ways to program the flash: in-system programming and in-application programming. In-system programming, or ISP, is programming of the on-chip flash memory using the bootloader software and UR0 serial port. This can be done when the part resides in the end user board. In-application programming is performing erase and write operations on the on-chip flash memory as directed by the end user application code. If you follow the flowchart, you will notice that it has two possible endings. If valid user code is present in the flash, the bootloader will transfer code execution to internal memory. If no valid code exists and port 2.10 is held low, then the ISP mode is invoked and the chip will look forward to ISP commands on the UART interface. Finally, the bootloader also provides CRP, which is code read protection, that enables the application to apply different levels of security. Memory Protection Unit, or the MPU. The MPU divides a memory map into a number of regions and defines the location, size, access permissions, and memory attributes of each region. It supports independent attribute settings for each region, overlapping regions, export of memory attributes to the system. The memory attributes affect the behavior of memory accesses to the region. The Cortex M3 MPU defines 8 separate memory regions, which are from 0 to 7. A background region. The background region has the same memory access attributes as a default memory map, but is accessible from privileged software only. In an OS environment, the kernel can update the MPU region setting dynamically based on the process to be executed. Typically, an embedded OS uses the MPU for memory protection. For more details on the MPU, please visit the appendix section of the LPC1700 User's Manual. Under key system blocks, we'll cover clocking, NVIC, and DMA support. Clock structure. The LPC1700 includes 3 independent oscillators. These are the main oscillator, the internal RC oscillator, and the RTC oscillator. Each oscillator can be used for more than one purpose as required in a particular application. Following reset, the LPC1700 will operate from the internal RC oscillator until switched by software. This allows systems to operate without any external crystal and allows the bootloader code to operate at a known frequency. Internal RC oscillator. The IRC may be used as a clock source for the watchdog timer and or as a clock that drives PLL0 and subsequently the CPU. The nominal IRC frequency is 4 MHz with an accuracy of ±1%. The accuracy of the internal RC oscillator is a key feature which may not be available with most of our competitor devices. Some side notes. The precision of the IRC does not allow for use of the USB interface, which requires a much more precise time base in order to comply with the USB specification. Also, the IRC should not be used with the CAN block if the CAN baud rate is higher than 100 kilobits per second. Main oscillator. The main oscillator can be used as a clock source for the CPU with or without using the main PLL, which is PLL0. The main oscillator operates at frequencies of 1 to 25 MHz. This frequency can be boosted to a higher frequency up to the maximum CPU operating frequency by PLL0. The main oscillator also provides a clock source for the dedicated USB PLL. RTC oscillator. The RTC oscillator provides a 1 Hz clock to the RTC and a 32 kHz clock output that can be used as a clock source for the PLL0, CPU, and the watchdog timer. Clock structure continued with PLLs. There are 2 PLLs in this system, main PLL and USB PLL. Main PLL, which is also called PLL0. PLL0 accepts an input frequency in the range of 32 kHz to 25 MHz. The clock source is selected in the clock source select register and it can use either of the 3 oscillators: the main oscillator, the internal RC oscillator, or the RTC oscillator. The input frequency is multiplied up to a high frequency and then divided down to provide the actual clock used by the CPU, peripherals, and optionally the USB subsystem. PLL0 can produce a clock up to the maximum allowed for the CPU, which is 100 MHz. USB PLL, which is also called PLL1. PLL1 accepts an input clock frequency in the range of 10 MHz to 25 MHz. PLL1 receives its clock input from the main oscillator only and can be used to provide a fixed 48 MHz clock to the USB subsystem. This is an option in addition to the possibility of generating the USB clock from PLL0. PLL1 is disabled and powered off on reset. If PLL1 is left disabled, the USB clock can be supplied by PLL0 if everything is set up to provide 48 MHz through that route. If PLL1 is enabled and connected via the PLL1 connect register, it is automatically selected to drive the USB subsystem. Clocking explained. Let's try to connect the dots by visiting this image from the user's manual. Let's take a step-by-step approach and we can examine each clock path in detail. C clock. As you can see, any of the three oscillators can be chosen to generate the sys clock which is needed for C clock. The main PLL and the CPU clock divider can then be used to generate the C clock. The 8-bit CPU clock divider allows a range of operations including slowing CPU operation to a low rate for temporary power savings without turning off PLL0. Also has a note, when the USB interface is used in the application, C clock must be at least 18 MHz in order to support internal operations of the USB subsystem. P clock. Now let's look at the derivation of the peripheral clocks. P clocks 1 to 4 are derived from the C clock, and there are 4 possible derivations: C clock divided by 2, C clock divided by 4, C clock divided by 8, or C clock itself can be directly fed to the peripherals. Peripherals have the option to select any of the 4 derivations, which offer them a lot of flexibility and helps the application to fine-tune the power consumption. Watchdog clock. Clock for the watchdog can be derived from 3 sources: IRC, peripheral clock or P clock, and the RTC oscillator. The clock source selection register can be locked by software so that it cannot be modified. On reset, the clock source selection bits are always unlocked. When the IRC is chosen as the watchdog clock source, the watchdog timer can remain running in deep sleep mode and can reset or wake up the device from that mode. USB clock. Finally, let's look at the USB clock derivation. As you can see, the USB block has its own dedicated PLL which is termed as PLL1. If PLL1 is enabled, its output is automatically used as a USB clock source, and the PLL1 must be configured to supply the 48 MHz clock to the USB subsystem. Clock out. For system test and development purposes, any one of these several internal clocks may be brought out on the clock out function available on port 1.27 pin as shown in the image. Clocks that may be observed via clock out are the CPU clock, the main oscillator, IRC oscillator, USB clock, and the RTC clock. This is again a key feature as you can use the LPC1700 to clock other units in the system as well. Now that we understand clocking, let's look at the key features of the nested vectored interrupt controller. The LPC1700 supports 35 vectored interrupts with programmable 32 priority levels for each interrupt. For when it comes to interrupt prioritization, grouping of interrupts and subgroups are also supported. An external non-maskable interrupt NMI, deterministic interrupt latency, we will see this in the next slide. Advanced features like priority preemption and tail chaining are also supported. NVIC interrupt latency. This is a key feature since interrupt latency in ARM7 is not deterministic. Cortex M3 has an interrupt latency of 12 clock cycles to enter and exit from the interrupt service routine. The tight integration of the NVIC with the processing core enables faster execution of ISRs, reducing the number of cycles typically taken to enter an interrupt by up to 70%. The image is showing the interrupt latency of the Cortex M3 core. NVIC interrupt tail chaining. Tail chaining technology in the NVIC supports interrupts that occur back to back, and there could be cases where an interrupt of higher priority occurs during the push and pop stages of the interrupt being serviced. In traditional interrupt-based systems, these stages need to complete before the pending interrupt can take over. As shown in the image, it would take around 30 clock cycles to jump from ISR1 to ISR2. The Cortex M3 NVIC, on the other hand, provides deterministic response to these possibilities with support for late arrival and preemption. In case of the late arrival of a high priority interrupt during the execution of the stack pop from a previous interrupt, the NVIC immediately fetches a new vector address to service the pending interrupt as shown in the figure. The interrupt latency in this case is just restricted to 6 clocks. The shown image is taken from the Cortex M3 white paper. Cortex M3 exception types. Shown on the slide are the exception types of the Cortex M3 core. The bottom 15 interrupts relate to the core itself. In this block, interrupts for reset, NMI, SysTick, and MPU can be found. After this block, the peripheral interrupts of the LPC1700 are positioned. Continuing on the same line of thought, let's look at the vector table of the LPC1700. Vector table starts at location 0, and the lower vectors relate to the Cortex M3 core as mentioned in the previous slide. Vector table contains addresses of exception handlers or ISRs. Main stack pointer initial value is in location 0, which is set up by hardware during reset. Vector table can be relocated to the SRAM via the vector table offset register. On the LPC1700, each interrupt source has a 5-bit interrupt priority value which helps in classifying the interrupt into groups and subgroups. The 5 bits are controlled by the pre-group field of the application interrupt and reset control register in the NVIC. The software programmable pre-group fields of the NVIC choose how many of the 5 bits are used for group priority and how many of them are used for the sub-priority or subgroups. Let's look at a few examples. If the pre-group value is 3, then the 5 bits are broken up into 4:1, where you have 4 bits for groups and 1 bit for subgroups or sub-priority. In this situation, you would have 16 groups in your system, and within each group you would have 2 subgroups. If the pre-group value is number 5, then the breakdown of those 5 bits will be 2:3, where 2 bits are assigned for groups and 3 bits are assigned for subgroups. In this case, there would be 4 groups in the system, and within each group you would have 8 sub-priority or subgroups. Finally, if the pre-group value is 2, then it will lead to a situation where all the 5 bits are used for groups exclusively. In this situation, you will have 32 levels of groups in the system with no subgroups. Here is an example that shows how to classify 2 interrupts into the same group but different subgroups. The examples in consideration here are the external interrupt 0 and the GPIO interrupt pins. The pre-group value chosen is number 4, which means you would have 3 bits for groups and 2 bits for sub-priority or subgroups, which will yield to 8 groups in the system, and within each group you can have 4 sub-priority levels. If you follow the example, you will see how both external interrupt 0 and the GPIO interrupt are assigned to group 0, but they fall under different subgroups. DMA support. Let's look at the key features of the DMA. As shown in the figure, the GPDMA block is an AHB bus master. It has 8 DMA channels with a forward FIFO per channel. The GPDMA block supports the following peripherals: SSP, I2S, UART, ADC, and DAC. The DMA can also be triggered by a timer match condition. As shown in the image, GPIO registers are now accessible by the GPDMA controller to allow DMA data to and from GPIO synchronized to any DMA request. Single and burst requests are supported. The table shows which peripherals support single request and which peripherals support burst request. Peripheral support. In this section we will cover the following topics: the 15 serial interfaces, timers, motor control block, analog blocks, and GPIO. With 15 serial interfaces, the LPC1700 series is simply a great fit for communication-intensive applications. The blocks within the red box highlight the different serial interfaces. Complementing these blocks are the Ethernet and USB interfaces, which are also set up as AHB bus masters. This slide highlights the key features of the SPI and SSP controllers. The SPI controller has a maximum possible speed of 12.5 megabits per second as a master or a slave. The SSP controller has a maximum possible speed of 50 megabits per second as a master and 8 megabits per second as a slave. The LPC1700 has got 3 I2C controllers. The I2C0 supports Fast Mode Plus. It is a standard I2C compliant bus interface with open drain pins. This interface supports functions described in the I2C specification for speeds up to 1 MHz. This includes multi-master operation and allows powering off this device in a working system while leaving the I2C bus functional. I2S is a standard interface used for audio-based applications, and this slide is listing the key features of the block that you can find on the LPC1700. There are 4 UARTs on the LPC1700. Let's look at some of their key features. 16-byte receive and transmit FIFOs with DMA support, fractional divider for baud rate control, autobaud capabilities and implementation of hardware and software flow control, 9-bit mode, which is a key feature, modem control support, IRDA support, and finally UART 1 has more features as compared to UART 0, 2 and 3. There are 2 CAN controllers which conform to the CAN specification version 2.0b. Data rates up to 1 megabits per second are supported on each bus. The blocks have an inbuilt hardware acceptance filter that can recognize 11 and 29-bit RX identifiers. Ethernet interface contains an Ethernet MAC with RMII interface, supports 10 or 100 megabits per second, 5 devices, dedicated DMA controller, and the block is fully compliant with the 802.3 standard. USB. The LPC1700 supports USB 2.0 full speed with device, OTG and host controllers, built-in on-chip PHY for device and host functions, and dedicated DMA controller. The table shows a clear picture of the different offerings in terms of on-chip controllers and PHY support. Let's check out the timer support in the LPC1700. There are 4 general purpose timers: watchdog timer, repetitive interrupt timer, PWM, and the SysTick timer. The general purpose timers are pretty straightforward, and the same block appears in all the ARM7 devices as well. This block has a total of 8 capture inputs and 4 external match outputs. The timer can be used as a counter to count external events. Timer events can selectively generate DMA requests. This allows for timed memory-to-memory transfers. The match output can toggle, go high, go low, or do nothing. We touched upon the watchdog timer in the clocking section. The block is enabled by software and it can be used in deep sleep mode when using the IRC as a clock source. A debug mode is also provided wherein the watchdog can just interrupt the core instead of a full-blown reset. The image on the right shows the different clock sources for the watchdog. Repetitive interrupt timer. The repetitive interrupt timer provides a versatile means of generating interrupts at specified time intervals without using a standard timer. It is intended for repeating interrupts that aren't related to operating system interrupts. However, it can also be used as an alternative to the Cortex M3 system tick timer. The PWM block can be used as a counter or in a timer operation. The 7 match registers allow up to 6 single edge control or 3 double edge control PWM outputs or a mix of both types. The block can be used as a standard timer if the PWM mode is not selected. Two 32-bit capture channels take a snapshot of the timer value and they can optionally generate an interrupt. Sys-tick timer. The sys-tick timer is an integral part of the Cortex M3. The system tick timer is intended to give a fixed 10 millisecond interrupt for use by an operating system or other system management software. The system tick timer is a 24-bit timer that counts down to 0 and generates an interrupt. The default values in the internal registers give a 10 millisecond interrupt rate if the CPU clock is set to 100 MHz. The system tick timer can be clocked either from the CPU clock or from the external pin STCLK. Motor control PWM block. The LPC1700 is equipped with a motor control PWM block that is optimized for 3-phase AC and DC motor control applications. The block can also be used for many other applications that need timing, counting, capture, and comparison. The motor control PWM block contains 3 independent channels, each including a 32-bit timer counter, a 32-bit limit register, a 32-bit match register, a 10-bit dead time register and an associated 10-bit dead time counter, a 32-bit capture register, 2 modulated outputs MCOA and MCOB with opposite polarities, a period interrupt, a pulse width interrupt, and a capture interrupt. The PWM outputs have opposite polarities and can be edge or center aligned. You can also include programmable deadband insertion. Feedback inputs are provided to automatically sense rotor position and use that information to ramp speed up or down. An abort interrupt is also provided that causes the PWM to immediately release all motor drive outputs. Here is an example of the LPC1700 being used in a motor control application. The LPC1700 is providing the PWM signals that drive the MOSFET driver. The right-hand image shows the different signals that the LPC1700 uses. Example of a MOSFET driver is shown as an edge bridge circuit consisting of 4 transistors. Based on the state of the transistors, the motors would change direction. The sensors will help in providing feedback to the LPC1700, and in the case of an emergency, the LPC1700 can invoke the abort command. The user's manual of the LPC1700 provides in-depth details for the different operating modes of the PWM block, so please be sure to visit this section when you refer to the document. The LPC1700 includes a Quadrature encoder interface or the QEI that neatly complements the motor control PWM block. A QEI, also known as a 2-channel incremental encoder, converts angular displacement of the motor into 2 pulse signals called Quadrature outputs, typically termed as phase A and phase B. They are called Quadrature outputs because they are 90 degrees out of phase. By monitoring the relative phases of these 2 signals, the LPC1700 can track the position and direction of rotation along with its velocity. In addition, a 3rd channel or index signal can be used to reset the position counter. The QEI has the following key features. It can track encoder position. A digital filter is provided with programmable delays for encoder input signals. The QEI can be programmed for 2x or 4x position counting. Velocity capture and index counter for revolution counting are key features. It can combine index and position interrupts to produce an interrupt for whole or partial revolution displacement. The LPC1700 includes a 12-bit successive approximation ADC with a measurement range of 0 to 3 volts, 12-bit conversion rate at 200 kHz, burst conversion mode for single or multiple inputs, optional conversion on transition of input pin or timer match signal, and DMA support are some of the key features. The image shows the 8 channels of the ADC with its individual match registers. Completing the list of analog blocks are the 10-bit DAC, POR, and BOD. The 10-bit DAC has a resistor string architecture with buffered output. The POR is pretty standard. The LPC1700 includes two-stage monitoring of the VDD voltage. If the voltage falls below 2.95 volts, the BOD asserts an interrupt signal to NVIC in order to cause a CPU interrupt. If the voltage falls below 2.65 volts, the BOD will assert a reset. This reset prevents alteration of the flash as operation of the various elements of the chip would otherwise become unreliable due to the low voltage. The BOD circuit maintains this reset down below 1 volt, at which point the POR circuitry maintains the overall reset. Let's look at the key blocks of the RTC domain. On the LPC1700, the RTC is clocked by a separate 32 kHz oscillator that produces a 1 Hz internal time reference. The RTC is powered by its own power supply pin, VPAT, which can be connected to a battery or tied to a 3-volt supply or can be left floating. 20 bytes of battery back storage that is especially useful when power is removed from the entire chip and the RTC domain is active. Let's look at the key features of the RTC block. Measures the passage of time to maintain a calendar and clock. Ultra-low power design to support battery power systems. Less than 1 microamp required for battery operation. 20 bytes of battery back storage. Dedicated 32 kHz ultra-low power oscillator with dedicated battery power supply pin. RTC power supply is isolated from the rest of the chip. RTC can work down to 2.1 volts. GPIO. Up to 70 high-speed GPIO pins are available in the LQFP 100-pin package, and up to 52 high-speed GPIO pins are available in the LQFP 80-pin package. All pins have configurable pull-ups and pull-downs. A new open drain mode is also available that applies to all GPIO pins. GPIO registers are located on a peripheral AHB bus for fast I/O timing. GPIO registers are accessible by the GPDMA. External interrupt inputs. Up to 46 edge-sensitive interrupt inputs are combined with up to 4 level-sensitive external interrupt inputs, which can optionally be used to wake up the processor from power down mode. Power management. Under the power management section, we will cover the following topics: power domains, power down modes, and the Wakeup interrupt controller. There are 3 power domains in the LPC1700, 2 of which are shown in the image on the right. A single 3.3 volt power domain between 2.4 and 3.6 volts. A VBAT pin which can operate between 2.1 and 3.6 volts. This is a key power domain since it allows turning off power to the bulk of the device while maintaining operation of the RTC. The 12-bit ADC domain which operates between 2.7 and 3.6 volts. Let's talk about the power reduction modes in the LPC1700. Sleep mode on the LPC1700 corresponds to the idle mode in the LPC2000 family. The name is changed because ARM has incorporated portions of reduced power mode control into the Cortex M3 core. In this mode, CPU execution is suspended and the peripherals continue to run. Wake up from sleep mode will occur whenever any enabled peripheral interrupt occurs. Deep sleep mode. Deep sleep mode on the LPC1700 corresponds to the sleep mode on the LPC2000 family. When the chip enters a deep sleep mode, the main oscillator is powered down and nearly all the clocks are stopped. The IRC remains running and can be configured to drive the watchdog timer, allowing the watchdog to wake up the CPU. The 32 kHz RTC oscillator is not stopped, and RTC interrupts may be used as a wake-up source. The flash is in standby mode, allowing a quick wake-up. The PLLs are automatically turned off and disconnected. The C clock and USB clock dividers automatically get reset to 0. The processor state and registers, peripheral registers, and internal SRAM values are preserved throughout deep sleep mode, and the logic levels of the chip pins remain static. The deep sleep mode can be terminated by either a reset or certain specific interrupts that are able to function without clocks. Power down mode. Power down mode does everything that deep sleep mode does, but also turns off the flash memory. This saves more power but requires a longer wake-up time. Wake-up from power down mode can be brought about by non-maskable interrupt, external interrupt, GPIO interrupts, Ethernet wake-up on LAN interrupt, BOD, RTC alarm interrupt, USB input pin transition, or a CAN input pin transition. Deep power down mode. In deep power down mode, power is shut off to the entire chip with the exception of the real-time clock, the reset pin, the WIC, and the RTC backup registers. Wake up from power down mode will occur when an external reset signal is applied or the RTC interrupt is generated. Wake up interrupt controller. The wake up interrupt controller enables the chip to wake up from deep sleep or power down mode without the use of the NVIC. It is completely controlled in hardware and no programming is required. A point to note here is that the wake up interrupt controller is only available in the release 2 of the Cortex M3 core. Tools and ecosystem. NXP has the best debug features on the LPC1700 series. Standard JTAG debug, serial wire debug and serial wire output pins, embedded trace macro cell for real-time trace, and support for up to 8 breakpoints and 4 watch points. Shown on the slide is a quick overview of the debug and trace pins that are available on the LPC1700. For evaluation boards, you will find low-cost evaluation boards from Embedded Artist, Hitex, IAR, and Kyle. Most of these vendors also promote their IDEs, so you can pick up any standard JTAG emulator that can support the Cortex cores. Complete listing of tools. Our team has assembled a comprehensive tools brochure that will enable you to quickly find the perfect tool and all the software packages that support the LPC1700 series. The tools brochure can be found by browsing to the More Information section at www.nxp.com/LPCZone. This brings us to an end of the LPC1700 product overview presentation. Please leave your feedback and any suggestions that you might have in the comment box. Your inputs will help us improve the training experience in the LPC zone. We are adding new training modules all the time at www.nxp.com/LPCZone. So we encourage you to register and we will send you email updates when new videos get uploaded. Thanks for watching this video and we look forward to seeing you again.